Students, today in this session we are going to see the standard type 1 PDEs and discuss the method of finding the solution of this standard type 1 PDE, which is given as follows. So this topic is coming under unit 2. Now, the previous session we discussed the PDE with simple cases where we use simply we use integration to find the solution of the PDE. But now we are going to study now what is a standard type 1 PDE. Standard type 1 PDE, which is of the form some function of P and Q equals to 0. That PDE will be of this format. That PDE will consist only involving P and Q alone. That kind of PDEs are classified as standard type 1 PDE. And now we are going to discuss the method of how to find the complete integral, singular integral, and the general integral. Singular integral does not exist for this type, that we are going to check now. First we will check what is the complete integral corresponding to this kind of PDE. The PDE will be involving only P and Q. Now let us consider the equation. Let us consider the equation. Let us consider the equation. Say Z equals to AX plus BY plus C. So let the given PDE, which is a function of PQ, let it be equation 1. Let us consider this equation. We call it as AX plus BY plus C. We give the name of this equation, number to this equation as 2, where A and B are connected by the relation. A and B are connected by the relation, where A and B are connected by the relation, say capital F of A comma B equals to 0. This one. See, this is the given PDE, which is capital F of P comma Q equal to 0. So if there exists a relationship like this between A and B, so this A and B are connected by this relationship, which is given by the PDE. The relation A and B. Now we are going to do differentiating. Differentiating the above equation, differentiating the above equation partially with respect to x and y. Partially with respect to x and y, we get. So what happens if you differentiate with respect to x partially? The left hand side is dou z by dou x, right hand side will become a. So we get p equals to a. And if you differentiate with respect to y partially, we get q equals to b. This is what we get from second equation. Substituting these values in the given PDE, substituting these in the given partial differential equation, we get the relationship called as f of a comma b equals to 0. So from the relationship, say capital F of a comma b equals to 0, we can find this b in terms of a. Say this b can be expressed as some function of a, if because that relationship exists, f of a comma b equals to 0. Substituting this in equation number 2, we get z equals to ax plus by plus, instead of b we are going to put pi of a y plus c. We name this equation as 3. We see that this equation 3 is the complete solution. It's called as the complete solution of the given PDE1. Why it is called a complete solution? Why this is called as a complete solution? Because the number of arbitrary constants is equals to the number of independent variables. Here x and y are independent variables. The number of constants, arbitrary constants involved is just a, and this is also a function of a and c. There are two different constants. And this is a solution of the given PDE, because this PDE, this 3 satisfies the given PDE, say 1. Hence we note that for a linear partial differential equation, for the linear partial differential equation of type 1, the complete solution is of the form say z equals to ax plus by plus c, where a and b, where this a and b are connected by the relation, say f of ab equal to 0. That is, we can find b in terms of a, or we can find b in terms of some function of a. Here this a and b are arbitrary constants. A and B are arbitrary constants. To find the singular solution, to find the singular solution, we need to determine the eliminant of A unit of A and C from z equals to ax plus some pi of a into y plus c. This is the complete solution, and differentiating this with partially with respect to a and c. So what we get, differentiating with respect to a partially, we get 0 equals to x plus pi dash of a into y, and c differentiating with respect to a is 0. And what is the other thing? We have to differentiate with respect to the other constant, say c. That is 0 equals to, and the right hand side I get 1. And this is an absurd result. 0 equals to 1 is an absurd result, because singular solution is nothing but the envelope of two parameter family of curves given by the complete integral, say z equals to ax plus pi of a y plus c. This z equals to ax plus pi of a into y plus c contains only two parameters. What are they? A and c, because there exists a relationship between a and b that we replace it by pi of a. So only two constants are involved. That is two parameter family of curves. This is a two parameter family of curves, and we need to find the envelope of this curve. How to find the envelope? Take the complete integral and differentiate with respect to one variable partially, and differentiate the same with respect to the other arbitrary constant, say c, partially, and the eliminant of a and c from these three equations, we get the singular solution. But for this type 1 PDE, we get an absurd result, say 0 equals to 1. So what is the final conclusion? There exists no singular integral for standard type 1 PDE. That is what is the conclusion. As the last equation is inconsistent, inconsistent, no singular solutions will exist for the type 1 PDEs. Type 1 PDEs. Now, how to find the general solution? Need to find the general solution now. So what is the procedure? Already we studied what is a single solution, general solution and complete solution. We take the complete integral from the previous step, that is the two parameter family of curves, and replace that c with some function of a. And hence this complete integral becomes a one parameter family of curve, and we need to find the envelope of that one parameter family of curve. Then the resulting that is called the envelope is called as the general solution of the given PDE. See, now to find the general solution, the complete solution, you have to take it. The complete solution becomes one parameter family, one parameter family, say z equals to ax plus that b becomes pi of a into y, and c also becomes some other function, we call it as psi of a. So this is a one parameter family of curves. So how to find the envelope of one parameter family of curves? So you have to differentiate with respect to the only one parameter available partially. So dou z by dou a, actually this is equals to 0. Right hand side will become x, because we are differentiating with respect to a partially, and this will become pi dash of a, and this will become psi dash of A. So now eliminating A from the above two equations, we get the general solution. Which is nothing but the envelope, which is the envelope. I already explained you geometrically what is envelope. Envelope of the single parameter family given by this equation. What is that? Z equals to ax plus pi of ay plus psi of a. And this completes the method to find the different solutions of type 1 PDE. Okay. Now we will go for the problems. So for a type 1 PDE, which is a function of P and Q alone, there exists no singular integral. We need to find the complete integral, immediately general solution or a general integral. Complete integral is of form z equals to ax plus by plus c. So the complete integral, we have to create a two parameter family of curve, and general integral is nothing but the envelope of one parameter family of curves. Sorry, we have to use the word envelope. Okay, now we go to the problem. So the question is, solve p square plus q square equals to 1. P square plus q square equals to 1. And this is the type 1 PDE. P square plus q square equals to 1. Say the first equation. Equation 1 is of the type, say, some function of p comma q equals to 0. This is type 1 PDE. We can see that it involves only P and Q. So therefore, what is the complete solution? Already we discussed. Therefore, the complete solution of this partial differential equation is of the form say z equals to ax plus by plus c. Complete solution will be of this form. Now differentiating to partially with respect to a and b, we get, so as already discussed in the method, if you differentiate with respect to partially with respect to a and b, we get p equals to a and q equals to b. So we get p equals to a and q equals to b. Therefore, we go and substitute in this first differential equation, we get a relationship between a and b. Therefore, using the above in equation, in 1, we get, because you replace p and q by a and b, so we get a square plus b square equals to 1. So which implies b square equals to 1 minus a square. So which implies b equals to plus or minus the square root of 1 minus square into plus or minus. So the complete solution is given by z equals to ax plus b. B is nothing but, we can put it here, plus or minus square root of 1 minus a square into y plus c. This is the equation number, and this is the complete solution of the given PDE. Okay, this is the complete solution because it contains only two parameters, a and c. The number of independent constants is also 2. So that is the definition of a complete solution, where a and c are arbitrary constants. There is no singular integral as discussed earlier. There is no singular integral to the partial differential equation to the PDE of standard type 1. To obtain the general solution or a general integral, we take c equals to some function of a. We don't know what is this function. We assume that c equals to a function of a. Then what happens to 3? 3 becomes z equals to ax plus or minus square root of 1 minus a square into y plus pi of a. This is equation number 4. So to find the general solution, we have to, this is a one parameter family of curves. This is equation 4 is one parameter, only one parameter a is involved, one parameter family of curves. So to find the envelope of this, we have to do the partial differentiation. Now differentiating partially with respect to a, we get, so what happens if we differentiate with respect to a partially? Dou z by dou a. Actually this is equal to 0 because z involves only x and y. So we are differentiating with respect to a, then becomes 0. So what happens to the first term with respect to a? It becomes x. So plus or minus as it is I write. So what is differentiation of square root of 1 minus a square? That is nothing but 1 by 2 times square root of 1 minus a square, and we get minus 2a in the top. So minus 2a, but anyway we can cancel this 2 and 2, so I simply erase this one. Minus a into y plus differentiation of pi function, pi of a is just pi dash of a with respect to, mean this equation as 5. So eliminating this a from 4 and 5 we get the general solution or general integral. So this concludes the point. If we know what is that c equals to pi of a, we can eliminate it. Otherwise we can simply write that a is, it can eliminate a between 4 and 5, we get the general integral. So this is how we approach this type 1 PDE and get the solution. There exists no singular integral. Complete integral, how to find the complete integral? So initially we assume that z equal to ax plus by plus c is the solution of the given PDE. Then from that we find the relationship between P and Q, sorry, A and B, and from that we find what is B in terms of A and substitute them in the assumed solution, we get the complete solution. Then there exists no singular integral, then we find the general integral or the general solution. Now we go to the next problem, problem number 2. Solve square root of p plus square root of q equals to 0. The equation is of the type the partial differential equation, say square root of p plus square root of q equals to 1. I name this as the first equation, is of type 1 PDE because it is involving only p and q, a function of p and q. So it's a type 1, the PDE is of type 1, so type 1, simply we can write type 1. The complete solution is of the form complete solution is of the form z equals to ax plus by plus c. So differentiating one partially with respect to a and b, we get p equals to a and q equals to b. Therefore, from 1 we get, substituting this above in 1, we get square root of a plus square root of b equals to 1, which implies square root of b equals to 1 minus square root of a, which implies b equals to 1 minus square root of a b whole square. So this is b. So this is b. We found the relationship between b, a and b. Now, actually this is the second equation. Therefore, using the above relation in 2, we get the general solution. We get the complete solution. We get the complete solution. Say z equals to ax plus b is nothing but 1 minus square root of a the whole square plus c. I name this equation as equation number 3. So now there exists no singular integral for this type 1 Pde. Now, how to find the general integral? I will put the heading as general integral. How to find the general integral? Let us take that constant c as some function of a. Therefore, what happens to equation number 3? It becomes ax plus 1 minus 1 minus 1 minus square root of a the whole square times y. I forgot this y here. Plus what is c? We have assumed pi of a. I name this equation as 4. Now what we do? Differentiating 4 partially with respect to a, we get dou z by dou a actually 0, which is equals to x plus so what is the differentiation of this quantity with respect to a? So n a n minus 1 n a n minus 1 into what is the differentiation of minus square root of a, so minus sign I put it here, into square root of a is 1 by 2 into square root of a. This is the differentiation of c. This is n a n minus 1 into minus 1 into what is square root of a differentiation 1 by 2 into square root of a times y, and this becomes, okay, once again I will write it, 0 equals to x, and this minus sign I can put it in the beginning. These two get cancelled, so 1 minus square root of a into 1 by square root of a times y plus pi dash of a. I name this equation as 5. Now eliminating a from 4 and 5, we get the general solution, general integral, and this completes the